Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullah. In this lecture, I'll be talking about about molecular docking as one of the chemoinformatics technique. Okay, molecular docking is the ability to position a ligand in the active site of a protein and calculate the specific binding affinity. Okay, molecular docking simply is just to place a ligand into the active site of a protein, and then we let the program or software to calculate the binding affinity of this of the ligand with this uh, target protein. Docking algorithm can be used to define ligands and binding conformations at a receptor site close to experimentally determined structures. So we can use molecular docking to predict the binding conformation of the studied ligand or molecules into the binding site of the protein, and the result will be a conformation or that very close to the experimentally determined structure. Also, docking algorithm can be used to identify multiple proteins to which a small molecule can bind. Also, there are so many servers, you just submit your ligand and then the algorithm will search for the proteins that could be targets or suitable targets for these ligands. Okay, the concept of molecular docking. Um, in molecular docking, we generate three-dimensional structure of the or 3D model for the protein and ligand of the interest. So that means here we need to yes, here we need to generate 3D structure or to obtain 3D structure of the protein and the ligands. Okay, and we know that how to obtain the or from where to obtain the 3D structures of the protein and ligands as we studied before. Yes, if you remember, we have shown that structure small molecules or ligand structure could be obtained from web databases such as PubChem, okay, Zinc, okay, all these databases. Or also we can obtain a ligand by simple sketching the ligand in drawing software or sketching software. Proteins are obtained from PDB, PDB, protein data bank. Okay, so that means the inputs of molecular docking are protein and ligands. Okay, so by rotating and translating the ligand, generate very many different possible conformations for the complex. Yes, in molecular docking, we use ligands, and those ligands are then when placed into the binding site. For example, if this is the binding site of the protein, and then we place the ligand in the binding site, okay, then we try to find a suitable conformation of the ligand that can bind the bindings in the binding site of the protein by rotating and translating the ligand in the binding site. I will explain those terms. Rotation is clear for you, but I will explain translation in the following slides. Okay. Then after that, after you place the ligand into the binding site, then you calculate the energy of each. Energy, which is Gibbs free energy, and it is delta G. It is measured in kilocalorie per mole. Kilocalorie per mole. Okay. Report the most favorable structures and energies found. So the outputs of docking are the binding energies and the different conformations of the ligands. Application docking is used molecular docking is used for high throughput virtual screening يعني for looking for actives. Okay, so that means if you have a big number of compounds, then you can run molecular docking of this big database against a specific enzyme or enzymes in order to get the active compounds by ranking the molecules according to their binding energies. Lead optimization, guiding rotational structure change. So that means if you have a specific compound, then you can generate different conformation of this compound and dock them against the specific enzyme, or you can do this by uh, adding different functional groups or substituents into your lead compound or to compound, then you dock in order to see the difference, the change, the effect of the change on the structure on the binding energy of this ligand. Here you can see this is the binding site, okay, of the yes, this is the here this is the binding site. So this is the protein and this our ligand. The docking simply insert this ligand into the binding site. Okay, then we calculate the binding energy. Okay, so this is the complex protein ligand complex. Okay, then if you zoom in, okay, you can see the inside it. This is the binding cavity or binding site. You can see your compound inside the binding site of the protein. Yeah, this is L is the ligand, as you see here. Sorry. Yes, this is the ligand, and yes, and P is the protein. Okay, and PL is the complex. Virtual screening. In molecular docking, we can run yeah, high throughput virtual screening. High throughput means very big number of compounds. So and this the virtual screening is the computational or in silico. In silico means using the computer. Analog of biological screening. This called high throughput screening. High throughput screening is an in vitro process. Okay, so using the real molecules against real enzyme in order to determine the affinity or the efficacy of those compounds or the activity of those compounds when interact with the enzyme or enzymatic target or protein. So virtual screening is the same, but it is run in on a computer. The aim of high throughput virtual screening or virtual screening, the aim is to score. Score means to determine the energy. Okay. To rank means to put in order or filter a set of structure using one or more computational procedures. So that means uh, you will have a big number of compounds, then you dock them against specific enzyme. After docking, you can get the binding energies of these compounds, and then those compounds could be ranked according to their binding energy. Okay, filter means sometimes we can use filters for to select or to select compounds. I mean, feature like specific structure feature. For example, you can select set your filter only for like 5-member drink, for example, or you can set your filter, for example, using a specific scaffold or skeletons. Okay. When we say one or more procedures. So that means that there are so many procedures for virtual screening, but here we are going to talk about docking as one method for virtual screening. Okay. Okay, so this will be seen in the next slide. Visual screening can be used to help decide which compounds to screen. For example, if you have, let's say, um, if you have, let's say, 10,000 compounds, so when you run virtual screening, you obtain like 10 compounds with good binding energy. So then you can select from those 10, for example, 10, those 100, you can select 10 compounds or whatever to test them experimentally. Those compounds could be obtained from the market or could be synthesized in the laboratory. So which libraries to be synthesized? So that means when you run virtual screening, you can select the top ranked compounds, okay, in the list. So if you will have like so many compounds, so you can select the first compounds, okay, to to test them experimentally. You can obtain them from the market, or you can synthesize. If they are not available, you can synthesize those compounds in the laboratory. Then you can test them experimentally. Then which compounds to purchase from external company? That's what I have said now. So that means you can, from these compounds, you can select the compound that you can purchase from the market. To analyze the results of an experiment such as high throughput screening. For example, you can run high throughput screening, then you can select your compounds, the active compounds. You can then analyze the results using molecular docking in order to study the binding interactions of those compounds in the specific enzyme. Components of molecular docking software. Typically, protein ligand docking software consists of two main components, and those can work together: search algorithm and scoring function. So any molecular docking software consists of those two components, and those two components are very important for the software to function. Okay, so here I will explain this in more details. Okay, so search algorithm generate large number of poses of a molecule in the binding site. Scoring function calculate a score. Score means binding affinity or binding energy of for a particular pose. Let me do this or explain this. Okay. Okay, let me erase this. Okay. For example, yeah, assume that you have this compound. Okay. Assume that you have this compound. Okay. This, for example, your compound. Okay. And you want to dock this compound or ligand into this enzyme. Okay. So, naturally or in reality or in real time, the compound, when gets into the binding site, it undergoes conformational changes. So it rotates, translates, whatever, in order to get to find the best fit into the binding site. Okay, the best fit into to this binding site. But in molecular docking, in order to mimic this these conformational changes, the software using the search algorithm, okay, search algorithm, the compound will generate different poses. We call them poses. Generates poses. These poses are conformations. So, for example, I can set in my software uh, uh, for this compound, I can ask the software to generate 10 poses for this compound. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so these 10, these are 10 conformations of this compound, only one compound. And the software, in the software you can generate as many as possible. For example, you can generate 100 conformation for this compound, and this give the possibility for having a good interaction with this with the binding side of the protein. So search algorithm, this is the role of the search algorithm, is to generate the different poses. Then the role of the scoring function scoring function is to calculate the binding energy of each compound. So here this will calculate delta G, or binding energy, in kilocalorie per mole for each compound. So this will have binding energy, binding energy, binding energy, and so on. Okay, and those energies will be ranked according to the would be ranked from the strongest to the weakest. Okay, so for example, in most of the software, energy is recorded as minus value. For example, like minus 10.5, for example, kilocalorie per mole. Then like let's say minus 10.2. Then for example minus 9.5, minus 9.1, and so on. So this will be the best energy. Okay, so this in the case that you have only one compound. For example, if you have like 100 compounds, and you want to perform docking for those 100 compounds, the software is going to do the same. For each compound, the software will generate poses as according to the setting that you want. For example, you can ask the software to produce more than 10 poses. Okay, but if the number of compounds is very big, you just give smaller poses, so more number of poses to reduce the calculation time. Okay, because this will take much computer time. Okay, so this how docking runs. So that means the input of molecular docking input are ligand and protein. Okay, ligands and protein. These are the input. The output are poses, these poses, and binding energy. Okay, for each pose. Okay, so this yeah, explanation for how molecular docking run, or how the search algorithm and scoring function is. The search space, how the software can, or the search algorithm works. The difficulty with protein ligand docking is in part due to the fact that it involves many degrees of freedom. Degrees of freedom means the possibility of the molecule to rotate, to move, okay, to translate, and so on. Yeah, degrees of freedom. Yeah, these are degrees of freedom. The translation, look, please focus on this, translation and rotation of one molecule relative to another involve 6 degrees of freedom. Okay, 6. That means I have translation, 3 degrees in the translation and 3 degrees in the rotation. Rotation, let's talk about rotation. So for example, you know that the molecule has 3-dimensional structure. So if this X and this Y and this Z, so if this my molecule here, okay, so the molecule can rotate along the y-axis or x-axis or z-axis. Okay, so these now are 3 degrees of freedom. 3 degrees of freedom. Rotation about the x-axis or y-axis or z-axis. This what we call rotation. Uh, Translation is not is different from rotation. Okay, translation is the movement along the axis, not the rotation. Yeah, for example, if this my compound here, so if the compound is moving along the x-axis, or it can move along the x-axis or y-axis just by sliding the compound. You can just take it this way or up or to the x-axis. Okay, so this is what we call translation. So translation, it could be along the y-axis or x-axis or z-axis. Okay, so these are 3 degrees of freedom, and these are 3 degrees of freedom. So the total is 6 degrees of freedom. Okay, so that means the compound is free to move through these or via these 6 degrees of freedom. Okay, within the binding side. I'm talking about the binding side. Okay. There is an addition. In addition, okay. So look at. Let me erase this. Okay. Now let's not to forget another degree of freedom, which is the conformational degree of freedom. Conformational degree of freedom is just linked with the rotation about sigma bond. Rotation about sigma bond. Okay, let me do it properly. For example, if you have if this your if this your compound, if this, for example, this atom, this another carbon atom, it's hydrogen. Yeah, assume that this compound is ethane. So rotation about this bond, okay, this is the conformational degree of freedom. Okay, so that means if the compound has more than one sigma bond, so that means there are so many conformational degrees of freedom. Okay, and this will generate different conformations of the compound. So conformations are generated only when there is a rotation about sigma bond. So these translation and rotation do not produce different conformation. They give the same compound, but conformation is due to rotation about sigma bond. Okay. To solve the okay, let me erase this. The solvent may also play a significant role in determining protein ligand geometry, often ignored though. Yes, sometimes the solvent, mainly here, the solvent used is water, so water normally is not considered during molecular docking. Okay. The search algorithm generate poses, okay. As I told you, poses means orientation and conformation of the compound. Generates poses, orientations, or particular conformation of the molecule in the binding site. So this is the role of the search algorithm, is to generate poses, orientations of the particular conformation of the molecule in the binding site. Search algorithm. We we can classify the various search algorithms according to the degrees of freedom that they may consider with respect to their ligand structure. So according to search algorithm, we have two types of molecular docking. We have rigid docking or flexible docking, and from the name here I can understand that rigid docking, so here we do not consider flexibility of the compound, and here we take flexibility into consideration. In rigid docking, the ligand is treated as rigid structure during the docking, and only translational and rotational degrees of freedoms are considered. So that means conformations are not considered. Conformational changes are not considered. So only translation and rotation degrees of freedom are considered. So that means just the localization of the ligand in the binding site. So in or out, up or down, left or right. So that means in, out, up, down, left, right. Okay, so that just we move the compound in, out, up, down, left, right only, but there is no rotation about sigma bond. Okay, to deal with the problem, for example, yes, let me erase this. Okay, to deal with the problem of a ligand conformation, a large number of conformations of each ligand are generated in advance, and each is docked separately. Yeah, here if for example you have just software that can run rigid docking, and you need to generate different conformations, so you can use another software to generate. For example, if you have this is your compound, this my compound, okay, this is your compound, and you want to run docking, and you have only rigid docking software. To solve the problem of conformation, you just use another software to generate different conformation. I mean, to rotate the different sigma bonds in order to generate like different conformation, like 1, 2, 3, 4 different conformations. Then you can use the docking software to dock each compound separately, okay, in order to get different a result of different conformation, docking of different conformation for the same compound. This indicates that your software cannot generate conformations for your compound. So that means you need to use, but this is not this problem nowadays is not found, because all the docking software can run or perform flexible docking. Okay, and you are not needed to do this. You're not needed to do this. Okay. Example for some softwares that perform rigid docking, and those are um, uh, these are softwares which are one of the oldest software that used in early times, like FRED. FRED means fast rigid exhaustive docking from OpenEye. This is the company that produces or develop this software. And one of the earliest docking program, which is one of the earliest, and those two software perform only rigid docking. Handling protein conformation. If, for example, you are using rigid docking and you want to consider the protein conformation, in this case, what you are going to do? Most docking software treat protein treats protein as rigid. Okay, we call this rigid receptor approximation. This approximation may be invalid for a particular protein ligand complex, as the protein may deform slightly to accommodate different ligand induced fit theory. You know induced fit theory? In this theory, for example, if this your binding site, for example, and this my ligand, for example, so uh, the protein will change the conformation to accommodate the ligand. Okay, so we call this induced fit theory. Induced fit. In induced fit theory, the protein binding site, the amino acid in the binding site undergoes conformational changes in order to accommodate, to receive the ligand, okay? Because this shape cannot accommodate the ligand, so the protein will deform slightly in order to accommodate the ligand. We call this induced fit, ligand induced fit. Protein side chains in the active site may adopt different conformations. So yes, they will change from this to this. The amino acids will change. The conformation will be changed. Okay. Some docking programs allow protein side chain flexibility. For example, we have a software like Autodock. Autodock software, you can select side chains of some amino acid and ask the software to allow this to undergo torsional rotation around acyclic bonds. Acyclic bonds means aliphatic bonds. Okay, so this will increase the search space. Search space means give more accurate results or give more results. Okay, so in this case, as mentioned here, in the binding site, you can select amino acid. Like you can ask the software to select alanine, let's say tyrosine, okay, let's say phenyl alanine, okay. So these amino acids will be you can select them and you ask the software to uh, to let them move or rotate. Okay, so this gives more accurate results than rigid docking. Large protein movement can only be handled by separate dockings to different protein conformations. So here, it's just by generating different conformation. For example, if you have this protein number 1, you can generate another protein with another conformation, and this another protein, and the same protein you can generate different conformations, and you then, for example, if this is your compound, you can dock your compound here, then you dock it here, then here, then here, then here, in order to get different results with different conformation. This will be the same protein. So this is the same protein. Okay, protein is it's the same protein, and this is the one ligand or so many ligands. You can dock your ligand in the different conformations of that protein. Okay. Pose prediction accuracy. Given a set of actives with known crystal pose, can they be docked accurately? Okay, let me tell you here one important thing, okay, about the crystal structure, protein crystal structure. Okay, when you download protein from protein data bank, the protein has, for example, is this your protein from data bank? In most cases, you find a ligand bind to this enzyme. We call this co-crystallized ligand. Co-crystallized ligand, which is co-crystallized with the protein. This co-crystallized ligand, originally it is an inhibitor, and it is complexed with the enzyme, and the complex undergoes X-ray crystallography imaging, and the structure is solved and uploaded to the protein data bank. Okay, and this enzyme, this ligand is very important for molecular docking, because it will be used when you are running docking. This ligand in the binding site, co-crystallized ligand, is used to direct your ligands into the binding site. So the software, if you have, for example, here a set of compounds, so the software will use this ligand in order to direct your compounds into the binding site. So that means the software will will know the binding site based on the co-crystallized ligands. So your ligands will be docked in this binding site because the software knows that this will be the binding site because of the presence of the co-crystallized ligand in the binding site. Okay. Now, how to know that my docking is or my compounds are docked accurately? Okay, before this, before docking, I have to do one thing. I have to redock this ligand, a main ligand from protein data bank or co-crystallized ligand. This should be redocked again. Okay, we call this process redocking or self-docking. Okay. Okay, let's read this. Accuracy measured by root mean square deviation. I will explain all these things, okay? Just let me read this. Accuracy measured by root mean square deviation compared to non-crystal structure. Root mean square deviation, square root of the average of the difference between a particular coordinate in the crystal and the coordinates in the pose. Pose means from docking, crystal means from protein data bank. Okay, so this will be like will be as follows. For example, you need to dock your compounds and compare your docking with the co-crystallized ligand. Yeah, for example, if this my enzyme, okay, and this my ligand, okay, so we call this co-crystallized ligand. This we call this crystal pose. Tamam, crystal pose. Okay, and then you can run redocking. Redocking means to take this ligand out, and then you redock it again, and then you run docking again. Okay, then you compare. So now this crystal pose, and we call this docking pose, because this generated from molecular docking, and this already obtained from protein data bank. Okay, it is raw data or raw structure. Okay, so then you overlap this with this. Superimpose them. You superimpose. When you superimpose them, you put them over over each other, the software will measure something called root mean square deviation. So that means the deviation from each other. This root mean square deviation indicates the accuracy of the docking. So the root mean square deviation should be less than 2. So 2 angstrom is considered a cutoff value. So that means if you got root mean square less than 2, so that means your docking is accurate. Your docking is accurate. Okay? So this is what we call pose prediction accuracy. Pose prediction accuracy. It's just you take the ligand from the binding site of the PDB crystal structure and redock this again. Okay, so this and then after that you superimpose the docking pose with the crystal pose, and you measure root mean square deviation. So this will give if you got value less than 2, so that means you have good docking. Now I will perform this using MOE software. I will show you how to do this, and I will end or stop this video or this lecture at this point, and then I will continue again. So now let me do this practically. Okay.